All right, so there is a mathematical formula that we're going to talk about. There's a term G. It actually, the reason that it's G is because, and it doesn't say it in this lecture, but it actually stands for Gibbs free. It's free energy, but it's Gibbs free energy. That's why it's a G. It's basically a measure of the energy that's available in a cell to do work. So a living system's free energy or a cell's free energy is the energy in that cell that's available to do work. It's not necessarily all the energy stored up in the cell, because some of the energy is tied up in places where it's not available. A kind of an example of this might be if, for example, the total amount of money I have might include my bank account, what's invested in my house, what's invested in my car, whatever. But I don't want to sell my house. I won't have anywhere to live. So my free energy might just be the cash that I have in my wallet. That's what I have right now that I can spend. And in a cell, it's the same way. The cell has some energy tied up in the parts of the cell that are keeping it alive. So the free energy is the energy in a cell that's available to actually perform work. Now, if you want to find out if a reaction is spontaneous or not, will a reaction proceed or will without the help of extra energy? The change in free energy, delta, if you remember from previous lectures, that just means change. By the way, G is always going to be a positive number because it's an amount. You can't have a negative amount of energy. You can have a negative change, though. And this is something that you have to be really careful with. A negative delta G. In other words, if you calculate, if you take the amount of energy in the products minus the amount of energy in the reactants, and the answer you get is negative, it doesn't mean that you have a negative amount of energy. For purposes of this formula, the negative has to do with the direction of energy. So if the energy is released by the reaction, if energy is given off, given away, you're going to have a negative delta G. And that's what we call a spontaneous reaction, a reaction that releases energy. If you have a positive delta G, that means energy has to be input. That's the amount of energy that's going to be required to run the reaction. So this is really important because a lot of people think the negative is, it's a negative amount of energy. You can't have a negative amount of energy. The positive and the negative in this formula refer to the direction. We're looking at a cell or a system. If the cell gives away energy, it's negative. It's given away, just like me spending money. It's a negative, it's taken away from my bank account. It's not a negative amount of money, it's just that the money left. I sent it somewhere else. And so that's the same thing here. Now another thing that cells can do, that's kind of unique with this, is that in a lab, if you recall doing chemistry labs, you might mix stuff in a beaker and the beaker gets hot. So you know that reaction gave off energy in the form of heat. You could feel it. In a cell, although some energy is released as heat, we think of heat as more of a waste product. What your cells can do, that's kind of unique, is that your cells can take energy that's being released from one reaction, capture it, and take it to a reaction that needs energy. So you may have a reaction over here that releases some amount of energy, and ATP is usually the chemical that does the carrying there. But ATP will grab onto that and, oh, great, you have extra energy. Great. I'll take it over to this other reaction that needs energy, and I'll use this extra energy to run that reaction. So the way that your cell runs reactions like the sodium-potassium pump is it takes energy from other reactions, ATP captures that energy, and then brings it over to run reactions that need it. So this is a way that your cell is able to manage its energy needs. It can get energy from spontaneous reactions that are releasing energy and carrying it over to reactions that need it. All right, so here's how you might get a problem from a graph. So here's an example. You have a reaction, A plus B makes 2AB. This is our reactants here. And this is our products here. So really, no trick questions here. The first question is, what is G, the amount of free energy in the reactants? So what is it from the graph? How much energy do the reactants have? 45, exactly. Really, and I know this doesn't go to the bottom. I messed up here. These should actually go all the way down. All right, so basically 45. And our units for energy, by the way, this graph is in kilojoules, but joule is the unit you're oftentimes going to see, joules or kilojoules for energy. The other unit you might see, although it's not the standard metric unit, is calories. So joules and calories are ways we measure energy. All right, so the G for the reactants is 45 kilojoules. What about for the products? About 25, right? It's supposed to be 25, so give or take. So 25 kilojoules. So to calculate delta G, it's going to be the amount of energy that the products have minus the amount of energy that the reactants have. So 25 minus 45, and so therefore what is delta G? Negative 20. Now, again, this does not mean that it made negative energy. The negative tells us the direction of the energy. That 20 kilojoules of energy is released by this reaction. And therefore, is this reaction spontaneous? Yes. Negative delta G, 100% of the time, tells me that the reaction is spontaneous. That's all you have to look for. If this number is negative, the reaction is spontaneous. Again, what does spontaneous mean? It means that the reaction doesn't require energy to proceed. In this case, it actually releases energy as it proceeds. If delta G is positive, that means the reaction is not spontaneous. It means you would need to input energy to run the reaction. So this is one type of problem you could see. You could see something from a graph where they could give you this information and then ask you, what is delta G and is the reaction spontaneous? And you can see it in the graph anyway. I mean, we can see that the amount of energy in the products is less. So that tells me that energy has been given off. This amount, this exact amount of energy, as a matter of fact, has been released somewhere. Could be released as heat, could be released as light, could be captured by ATP. But it's left the reaction and gone somewhere else. All right, there's one other formula that you can be given, and that is this one. And this is also, again, on the formula sheet. So we can also calculate delta G from other information. Again, these definitions are slightly different than the definitions you get in a chemistry class. So remember, delta G is a measure of how much free energy our system has, or the change, I should say. The change in free energy. Delta H, for the purposes of our class, is going to be the total energy of the system. In other words, how much energy the cell has in total. The free energy plus other energy that may not necessarily be available to do work, but is stored by the cell. T is our temperature. Remember that you have to add 273. This is Kelvin, just like in the previous chapter, the formula we learned. And remember, S, from the previous slide, is entropy, or the measure of disorder, the change in disorder. In other words, is this reaction building something that's more orderly? You know, something that's more complex? Or is it breaking something down and making a bunch of little molecules, which is going to be an increase in entropy? Because a bunch of little things bouncing around are going to have more entropy than building something complex and organized. So here's a sample problem. Again, you would have the formula sheet in front of you. It would just be a matter of plugging in numbers. So they give you delta H, delta S, and they give you the temperature. The only thing, remember, they kind of mess with you a little because they give you the temperature in Celsius, and you do have to convert to Kelvin. So they want you to calculate delta G and then say if the reaction will be spontaneous. Again, you're going to solve this exactly the same way that we did in the previous problem. To determine if it's spontaneous or not, you're just looking to see whether the answer you get is positive or negative. So we plug in our numbers. Delta H is 5,000. T is 25 plus 273, so that's going to be 298. And delta S is 20. If you multiply that out, I believe you get negative 960 kilojoules. So would this be spontaneous? Yes, it would. So this reaction overall gives off energy. Again, spontaneous, all it means is that a reaction does not require energy. in order to proceed. So it basically tells us this is the natural direction the reaction would go. It doesn't necessarily mean it'll get there very quickly. I mean, technically, me being a pile of ashes would be more stable and have more entropy than me being a living thing. But I don't spontaneously burst into flames. So just because spontaneous tells me the natural direction that things would go, but it doesn't necessarily mean that's what's going to happen. There could be other things preventing that from happening.
So is diffusion an example?
Diffusion is spontaneous, exactly. It doesn't require you to add any extra energy. You drop the food coloring in there, and it just goes on its own and it spreads out. So that would be an excellent example of a spontaneous reaction. All right. So spontaneous processes, again, at the top, you have a high potential energy. At the top of the diving board, you go into the water. That would be, you would have less potential energy, so that would be spontaneous. Diffusion would be an example. You go from being organized to increased entropy, less organized. And breaking something down, a chemical reaction that takes something really complicated and breaks it into a bunch of little things, this definitely has more entropy or disorder than the complex thing. So these are all examples of spontaneous processes. So to summarize what we already said, reaction with a positive delta G will be non-spontaneous. It will require energy in order to proceed. And a reaction with a negative delta G will be spontaneous. It tells us the direction that the reaction would naturally go. Doesn't mean it'll be fast, because there's another thing that we haven't talked about yet. Now, and we only have one more slide, by the way, and then we're done for today. You could, in some cases, tell whether a reaction is going to be spontaneous or not just by the signs on the different variables. For example, if delta S is negative, which means we're basically decreasing entropy. We're making something that's more orderly. So if we make this a negative number, and delta H is positive, so we're increasing the total energy of the system. So this is a positive number. Will delta G be positive or negative? It makes no difference what numbers I actually plug in. Delta G will always be which one? Positive or negative? No matter what numbers I plug in, if I'm decreasing entropy and increasing the total energy, if this is negative and this is positive, I will always have a positive delta G, which means that it requires energy, that this is not going to be spontaneous. So technically, anytime your cell is building stuff, it's not going to be spontaneous. It's going to require energy. What about the opposite situation? What if delta S is positive? So now I'm increasing the entropy, so I'm making things more messy, less organized. And delta H is negative, so I'm decreasing the total energy. No matter what numbers I plug in this time, if this is negative and this is positive, my delta G is going to be what? No matter what, right? Because this is going to be, this answer to whatever this is going to be a negative number, and this is a negative number. So this is always going to be spontaneous. So sometimes reactions will always require energy or not require energy. The thing is, sometimes you have a mixture, like this one. If both terms are positive, if delta S is positive, and so is delta H, this is possible, then we don't know if delta G is going to be positive or minus or negative. We don't know, because it's really going to depend on how big our numbers are. If delta H is a really big number, it's going to tend to make delta G negative, so it's not going to be spontaneous. Whereas if delta S is a really big number, it's going to tend to make it a spontaneous reaction. But here's one thing that you might notice. What's going to tend to happen to delta G in this situation if I make the temperature really high? I make this number really big. What's that going to tend to do to delta G? It's going to tend to make it more negative, which is why a lot of times we can get reactions to go by heating them up. Some reactions are spontaneous, but only at higher temperatures. If you heat paper hot enough, paper will burst into flames and burn. What? So for higher temperature is going to tend to make reactions more spontaneous. Not necessarily every reaction. Now here's the problem though. obviously in your cells, we can't increase the temperature too much or you'll kill the cells. So we have to have